Let's solve systems of linear first order ODEs. I want to point out that there are three cases that we're going to look at, and each of these cases has a unique way of solving it. The first case is the case where you have distinct eigenvalues. The second case is where you have repeated eigenvalues, and the third case is where you have complex eigenvalues. We're going to start with a problem where you have distinct eigenvalues. So in this video, it's just going to focus on distinct eigenvalues. The problem is dx dt is negative x plus 7y, and dy dt is negative 4y. Okay, so we can rewrite this equation as, let's see, let's rewrite it in matrix form. We can rewrite it as dx dt is equal to a x in this form, right? Or let's look at it this way. X dx dt, so dx dt dy dt is equal to, our a in this case is negative 1, 7, 0, negative 4. And then we have x and then y. Okay, so if we want to be very detailed, this is our dx dt, this is our a here, and this is our vector x. A is a matrix. All right, so what we're going to do, we're going to go step by step. This video is just going to focus on the method of solving it, and we're going to try to avoid as much details as of the theory as possible for the sake of time. So the first thing we do, the first step is step 1. We find the eigenvalues of A. Okay. If you've taken linear algebra, you can actually easily tell what the eigenvalue of this kind of matrix is. But let's solve it together. If you've been paying attention, if you were in the class, you will know that we have a method for solving the eigenvalues of a 2 by 2 matrix. This method only applies to 2 by 2 matrix. So we're going to, and the method is to solve lambda squared minus the trace of A plus the determinant of A equal to 0. Again, this equation only applies to 2 by 2 matrix. Once you have a 3 by 3 matrix or 4 by 4, it goes out the window. So this is the same thing as lambda squared. The trace is negative 1 plus negative 4, which is negative 5. So minus the trace will be plus 5 lambda. Then the determinant seems to be 4. Negative 1 times negative 4 plus or minus 0 times 7. So we have 4 is equal to 0. Can we factor this? Let's see. Can we? We can factor it as lambda plus 4, lambda plus 1. Okay, so this tells us that our eigenvalues are lambda equals 1 and lambda actually negative 1 and lambda equals negative 4. These are our eigenvalues. All right, so we found our eigenvalues. then the next step is to find the eigenvectors. Eigenvectors of A. All right. So for each of the eigenvalue, we have to find the eigenvector. Again, how do we find the eigenvector? We need to solve the equation. Solve A minus lambda I V is a vector is equal to 0, the 0, 0 vector. So this implies that we're solving A minus lambda I is, what is our A? A is negative 1, negative 7, 0, negative 4, minus lambda I will be negative 1 minus lambda, and then 7, and then 0, and then negative 4 minus lambda. Okay, and then V1 and V2 is our vector V is equal to 0, 0. Okay, so that's what it boils down to. And we're going to do this for each of our eigenvalues. So when lambda is negative 1, what do we get? We get negative 1 minus 1, negative 1 minus 1, or minus negative 1. Yeah, that's 0, right? 0. That is 0. And then we have 7, and then we have 0 here. And then we have negative 4 minus negative 1. That's negative 3. Okay. So we have V1 here, V2, and that is equal to 0, 0. All right, so this is interesting. Why is it interesting? Because we get two equations here. We get two equations that look kind of simple. 7V2 is equal to 0, right? This tells us that V2 is equal to 0. Once 7V2 is equal to 0 and negative 3V2 is equal to 0. So this just tells us that V2 is equal to 0. This doesn't tell us anything about V1, right? So if V2 is equal to 0 and V1 we have no information about V1, then V1 can be anything at all. All right? But whenever you get anything, the best thing to do is to assign it the value 1. Okay? So this tells us that our eigenvector in this case, this is the vector V. In this case is V1 is 1 and V2 is 0. Okay? Before we solve the next, we'll find the next eigenvector. Let's see. I want to mention something. We found our eigenvalues to be negative 1 and negative 4. And if you go to the matrix, you see that the main diagonal is negative 1 and negative 4. So this is always the case whenever you have a matrix where the lower part of the matrix is all zeros, right? Then the diagonals will be the eigenvalues. So this kind of matrix is called a triangular matrix, upper triangular matrix. When you have an upper triangular matrix, the diagonals are the eigenvalues. It actually also applies for lower triangular matrix, whereby you have 0 maybe over here, and you have 0 all above the diagonal. And then in that case also, the matrix diagonals are the eigenvalues. Okay, so let's go back to the second step. That was step 2. So we've done for lambda equals 1. We're going to do for lambda equals negative 4. So for lambda equals negative 4, what do we get? we get negative 1 minus negative 4. That's going to give us 3, I think. We have 7. And then we have 0, and we have 0. Okay. So this is V1, then V2. And this is going to give us 3V1 plus 7V2 is equal to 0. What does this mean? This means that V2 is equal to negative 3 over 7 V1. And then our eigenvector in this case is V is equal to, if we pick V1 to be 1, and then V2 is negative 3 over 7. Okay, so these are our eigenvectors. Eigenvector. First eigenvector corresponding to eigenvalue negative 1. Second eigenvector corresponding to eigenvalue negative 4. So we've solved the system. No, we haven't. We've only found the eigenvalues and eigenvectors. All right. So in general, for repeated eigenvalues, or for distinct eigenvalues, let's say lambda 1 and lambda 2 with eigenvectors, let's call them V1 like this and V2. Okay? The general solution is x is equal to C1, where C is a constant, C1 V1, vector V1 e to the lambda t plus C2 V2 e to the lambda t. Okay. So mind you, if we have, assuming we're doing 3 by 3 matrix, and we have, let's say we have 3 distinct eigenvalues, then the solution will just be plus C3 V3 e to the lambda 3 t. Sorry, this is lambda 1 and lambda 2. And so forth, if you have 4 by 4 and so forth. All right, but in this example, we're dealing with just 2 by 2. So let's go back to our problem. So our general solution is x of t, x is a vector, C1 e to the lambda 1 is negative 1 t, and then the eigenvector corresponding to that is 1, is 1, 0. Yep, 1, 0, 1, 0 plus C2 e to the negative 4 t, and the eigenvector corresponding to that is 1, negative 3 over 2. Okay, so let's see. This is what we have. Another way of writing it is that x of t in the equation is C1 e to the negative t plus C2 e to the negative 4t, right? And y of t is C1 e to the negative t times 0, so it's just 0 there. So you see what I'm doing here? What I'm doing here is, yeah, we have that. And then, so the first component of y is 0. The second component is going to be negative 3 over 7 C2 e to the negative 4t. So you can see this as the two solutions. Okay. Now, I want us to note a few things. Let's note a few things. We've studied fundamental solutions. So the fundamental solutions here, the fundamental set of solutions is e to the, let's do this, 1, 0, e to the negative t, and 1, negative 3 over 2, e to the negative 4t. Okay? So those are the fundamental, that's the fundamental set of solutions. Okay? Those two solutions form a fundamental set. And this fundamental set, let's look at another thing. This fundamental set, they're linearly independent, right? Linearly independent. Or, first of all, to show that, let's compute the Wronskian. So the Wronskian here, we don't need to take the derivative like we did when we're doing the Wronskian for just one differential equation. All we just need to do is to make each of the solution the column of a matrix. So we have the first matrix is, the first vector is 1, 0 times e to the t. So it's 1 times e to the t, e to the negative t. That will be e to the negative t times 0 times e to the negative t. So this right here, this whole thing is that. All right. And we do the same thing here. Multiply each 1 and negative 3 over 7. It's 3 over 7, not 3 over 2. By e to the negative 4t. So we have e to the negative 4t. And then we have negative 3 over 7, e to the negative 4t. Okay? So this Wronskian is just the determinant, right? The Wronskian is e to the negative t times negative 3 over 7 e to negative 4t, I think, minus 0 times e to negative 4t. All right, so this is just going to give you, negative 3 over 7 e to the negative 5t, which is not equal to 0. So in general, we can see that the fundamental set is, let's do the fundamental solutions are linearly independent, okay? Because their Wronskian is not equal to 0. Okay. Right, so we've solved the system. I want us to do something else. Let's now try to solve the initial value problem. Let's do the same problem, but let's now make it an initial value problem. So solve this problem. Ooh, let's see. But now it's an initial value problem. Isn't that fantastic? So paste here. Let's solve this same problem, but make it now an initial value problem. What are the initial conditions? The initial conditions, let's say x of 0, y of 0 is equal to 2, 3. All right. So since we already solved the problem, we're just going to go here and take this and solve for our C1 and C2. Remember, initial value problem is you solve the equation and then you solve for the constant using the initial conditions. So let's see, if we take this and we plug in zeros for t, we get x of 0 is equal to c1 e to the power of negative 0. So it's just c1 plus c2, and this is equal to 2. And then y of 0 is negative c2, right? Negative 3 over 7 c2, and this should be 3. So if you solve this, I'll let you solve it yourself. But if you solve this, well, first of all, you see that c2 is negative 7 easily. c2 is negative 7, and I think c1 is 9. Check this and correct me. I didn't. From here, I could see that c2 is negative 7. c1 is 9. I think so. I might be wrong, but correct me. If I'm wrong, let me know. Okay, so we found our thing. What did we find? We found our C1 and C2. So the solution, we can use this to write the solution to the equation. Let's write it in this form. Instead of C1 and C2, let's now change. Let's call it the particular solution. So the solution of the IVP is remove this C1, remove this C2, replace them with what you got. That's all. C1 is 9, so let's put 9. Do we put 9 here? Let's put 9 here. You could also decide to distribute the 9s into the vector, but let's just leave the 9 there. And then C2 is negative 7, so let's put negative 7 over here. Okay. All right, so that's our solution. Or how about this? We can also decide to write it as x of t is equal to 9e to the negative t minus 7e to the negative 4t, and y of t is equal to 3. This is 3 over 7. I don't know what is wrong with me. So it's just going to be 3, because negative 7 over here, negative 7 times negative 3 over 7 is just going to be 3. 3e to the negative 4t. Okay. All right. I want to sketch the solution. If you sketch this solution, I'm not quite sure about this, but I'm pretty sure about it. See, I have to choose one. Am I sure or am I not sure? But I think this is what the graph looks like. In class, we'll try to do it in Matlab. I'll show you how to do it, how to graph the solution in Matlab. So let's see, this is solution. All right, so let's graph x of t. X of t is x of t actually looks like this. So this is 1, this is 2. X of t looks something like this, like that. That's what it looks like. And then y of t looks like this. Okay. All right, so this is x of t. No. X of t. And the red one is y of t. Okay. So So I don't expect you to be able to sketch it by hand the way I just did. I'll teach you how to sketch it with a software. Okay. All right. The third thing I want us to do, you know what? I'm going to call this one. Let's call this A. Call this one A. And then let's call this B instead of calling it 1B. Instead of calling it number 2, let's call this 1B. So 1C is something that I actually like. I want us to draw the face portrait. I'll teach you how to do that. Draw the face portrait of the equation. Okay. We learned how to do direction field, and we learned how to do face portraits for a first order differential equation. Now, this is a system of equation, system of two first order equations. So we have x. The first thing we want to do is to draw our axis. We're going to have the x-axis. This is x of t. No, x of t. Yep. And then that's x of t, no. And this is y of t. Okay. Okay. So I'm going to move this over here. I want us to note a few things. The first thing I want us to note is that if you look at this equation, look at the equation. All right. The right-hand side, let's copy this. Copy. Paste it over here. So the fixed point, let's look at the fixed point first before we even go to draw. Oh, no, I don't want that. Come on. All right, I just want to copy this, move it out of the way. All right, so let's go back to our equation. This equation, let's try to find the fixed point. Stay with me. Right, to find a fixed point is when both sides is equal to 0. Remember fixed point or equilibrium point. We did it. Equilibrium point, fixed point. Let's see. Equilibrium points or fixed point. Fixed point occurs when both the x dt and dy dt are equal to 0. So this occurs when, so this is when we have negative, the right hand side of each of them equal to 0. Essentially, x plus 7y and negative 4y, this is equal to 0, this is equal to 0. So we have a system of equation that both sides are equal to 0. Both sides are equal to 0, and the determinant of the corresponding matrix is not equal to 0. Determinant of A, remember that our A is equal to negative 1, 7, 0, negative 4. And the determinant of A is 4, is not equal to 0. Right? Therefore, thus, the only solution to this, the only fixed point, in other words, the only solution to this is That's the solution to. I'm going to call it, give it my favorite name. I'm going to call it asterisk. Solution to asterisk over here is 0, 0, because the determinant is not equal to 0. All right, so we expect our fixed point to be 0, 0. And I'm going to mention something. Even the graph I sketched above shows that it's 0, 0. X of t goes to 0 as time goes to infinity. Y of t goes to 0 as time goes to infinity. Equilibrium point is the point that the system goes to as time goes to infinity. So what do we have over here? If we have this is our x-axis and that as our y-axis, and this as 0, 0, x 0, y 0, that means any trajectory should try to end up there. So what are we going to do? We're going to start by sketching our eigenvectors, right? The first eigenvector we have is 1, 0, right? And it corresponds to the eigenvalue, -1. So I'm going to draw that eigenvector. The eigenvector 1, 0 is x is 1 and y is 0. So this is your eigenvector here. But I'm not going to stop there. I'm just going to draw a line on the straight line that this eigenvector lives on. Okay? So that's our first eigenvector. The next eigenvector is the eigenvector 1, -3 over 7. So I'm going to do it a little different. I'm going to call it, well, 1, -3 over 7. So we have -3 over 7. Well, this 1, -3 over 7. All right, so it's going to be somewhere here. So we have this, I think. All right. Okay. So I'm going to draw a vector. First of all, I want to take something back. I want this, I don't want to put an arrow there. All right. This is the vector. I'm going to end it with an arrow, but I don't want this arrow. And I'll tell you why I don't want it. So I'm going to get rid of the arrow, okay? But I'm going to extend the vector all the way along the line it lives on. So the next vector is 1, -3 over 7. -3 over 7 is somewhere here, okay? So we have this, okay? So this is another vector, right? But I'm not going to include the arrow. I'm just going to leave it like that. Then what am I going to do? I'm going to extend this vector on the line it lives on. Oh, that's not a straight line. On the straight line it lives on, all right? I'm going to keep extending, All right, extend as much as we can. It doesn't seem like it passed through the origin. It's supposed to pass through the origin. That doesn't look straight, but it's good enough. I'm going to compress this. Okay, this whole thing is supposed to pass through the origin, so I'm going to cheat. I'm going to make it pass through the origin. Like this. Put this over there. That's our origin. Okay, so that's the first eigenvector and the second eigenvector, the lines that they live on. Okay, now, I'll now tell you the reason why I don't want the arrows. The arrows, in this phase portrait, arrows mean a lot. If the eigenvalues are negative, the arrows should point inwards. And the eigenvalue corresponding to the eigenvector 1, 0 is -1. So these arrows arrows should point inwards along that eigenvalue, inwards towards the origin. All right, another eigenvalue is -4. So these arrows should also point inwards along the lines on which along the line on which the eigenvalue lives. So now what do we know? We know that, let's label a few things. We know that this line contains the eigenvector 1, -3/7, and the eigenvalue here is -4. And this line contains the eigenvector 1, 0, and the eigenvalue is -1. Now, what we now do is we look at these two eigenvalues. The magnitude here, the magnitude of the eigenvalue here is 1. The magnitude of the eigenvector here is 4. When I say magnitude, it just means the absolute value. Now, if you are a trajectory, if you start somewhere, let's think of our trajectory that starts at our initial condition is when x is 2 and y is 3. X is 2, y is 3, I think. Okay? So let's assume we're starting at 2, 3. 2, 3 is somewhere well, we may not have 2, 3, but let's get another initial condition. Let's just get something over here. Okay, I'm going to say something. Remember this. Whenever you have a point, the point has to go towards the origin because the origin is equilibrium point. All right? In going towards the origin, it starts out being parallel to the eigenvalue that has the eigenvalue with a larger magnitude and ends up being asymptotic to the eigenvalue that has the smaller magnitude. What do I mean? So I have this point over here. This point, if I start out at this point, I'm going to start out being parallel to this eigenvector. This eigenvector. I might have said eigenvalue. And then I'm going to end up being asymptotic to this eigenvector. So I'm going to start out being parallel to that one. Let's see how that goes, like that. Then I'm going to end up being asymptotic, trying to behave like the one with a smaller eigenvalue. And I'm going to go towards the origin. So this means that if I start over here, assuming this point is, let's say this point is when x is, I'm going to call s 0.9 and y is 1.5. So if I'm a trajectory and I start here, I'm going to end up there, right? Remember, every trajectory goes towards the origin. So if I'm over here, if I start over here, for instance, I'm going to try to be parallel to the eigenvector corresponding to the eigenvalue with the larger magnitude, and then I'm going to become asymptotic to the eigenvector that corresponds to the eigenvalue with a smaller magnitude. So how do I go? I'm going to go like this, like that. All right. So the same thing over here. If I start over here, I'm going to try to be parallel to the eigenvector 1, -3/7, because 4 has the larger magnitude, and then I'm going to become asymptotic to the other eigenvector. So I'm going to go like this, like that. No. Like this, something like that. Okay, like that. Okay. And I'm going to use an arrow to demonstrate the direction of all the trajectories. All right. So this is a 2D phase plane. 2D phase plane. All right. So this is the initial condition and it goes towards the origin. So we call this kind of behavior a stable behavior. So 0, 0 over here. Let's make some notes. The origin here is a stable fixed point or stable equilibrium point, right? And this happens when both eigenvalues are negative. Okay? What else do we notice? 0, 0 is called a stable node or a sink. It's called a sink. All right. So that's all I want to mention about that. Let's see what else. So this happens when both eigenvalues are negative. All right. So I'm going to do another, let's see. So let's call this nodes number 1. Note number 2. You know what? Let's put number 2 over here. When both eigenvalues are positive, you get the same kind of behavior or the same kind of picture, but the behavior is different. 0, 0 is still going to be your fixed point. And assuming you got 1 and 4, right? You will get trajectories of this form, like this, like that, and then maybe like this. Oh, no, I don't want that. Like this, like that. But instead of pointing towards the fixed point, they're pointing away from the fixed point. They're going to be pointing away from the fixed point because they're not going to be going to 0. In that case, your graph is not going to be going to 0. Your graph will be going like this, to be maybe starting over here and going to infinity, right? Something like that. So that's the reason why they go away from the origin, okay? All right. Now, if you have two, let's say you have one negative eigenvalue one positive, then you have a behavior that is a little bit more interesting. Remember here that you still have your eigenvectors. Let's say we still have our eigenvectors at here and there. All right, they live on those lines. Okay, so let's say you have your eigenvectors on this line, but since they are, let's say this one is negative, so they're pointing inwards, and then you have one that the eigenvalues are positive, so they're pointing outwards. No, outwards. And we still have the 0, 0 is our fixed point. So what do we have? The trajectories are going to be they're going to be undecided. So if you have a trajectory that starts here, over here, the the trajectory is going to want to go to the fixed point, 0, 0. But then this eigenvector over here, one of the eigenvectors is going to be attracting it towards the fixed point, the eigenvector where that has the arrow pointing inwards, and the other eigenvector is going to be pushing it away from the fixed point. So we end up with something like that. All right, end up with something like this also. Okay, like that, like this. The same kind of thing happens here. You have that, the same kind of thing happens here. Okay, all right. So mind you, we're dealing with the case where you have two eigenvalues, and the two eigenvalues are both real and distinct. Distinct eigenvalues, distinct and real eigenvalues. Two eigenvalues, two real numbers, and they're both different. So we've looked at the case in detail. We looked at the case where both of them are negative, and we talked about where both of them are positive. This is how they behave, and where one is positive and one is negative. Okay? But what I want you to also take away is the method here of solving the solutions, of finding the solution, the general solution, and the particular solution when you have the initial condition. Okay? And then the third thing we did is how to sketch the face portrait, which is very interesting. I really like this. All right, so in the next video, I'm going to show you how to do this kind of thing when we have repeated eigenvalues. But before then, I want to give you one to try. Okay? All right, so let's call this example 2. Example 2. So we have dx dt is equal to negative 4x plus y plus z. All right, dy dt is x plus 5y minus z. And then dz dt is equal to y minus 3z. Okay, so this is a little different. I want you, A, to find the solutions, find the general solution. Just the general solution is fine. Find the general solution. So I want to make a few notes here. And this is something I've said before. Lambda squared minus trace of A plus lambda plus determinant of A equal to 0. This does not work here because it's 3 by 3. Does not work here. Does not work here. I don't work here. Why are you asking me questions? I don't work here. All right, so it doesn't work here. So you have to use the definition of eigenvalues. You have to use determinant of A minus lambda I is equal to 0. You have to compute the determinant of A minus lambda I and set it equal to 0. What is I in this case? What is I? I here is the identity matrix, identity 3 by 3 matrix, 1 0 0 0 1 0 0 0 1. Okay? So to find the eigenvalues, you really have to use this. Find the determinant of A minus lambda I, set it equal to 0, solve for lambda, and then you get 3 different lambdas, and then you compute the eigenvectors for each of the lambdas. The first lambda, you find the eigenvector. The second lambda, you find the eigenvector. The third lambda, you find the eigenvector. So here you're going to find your eigenvector. a vector with 3 components, another vector with 3 components. What are the vectors? The vectors are going to look like that. Three entries for each of them. Okay, they're going to be distinct eigenvectors, distinct eigenvalues, and different eigenvectors. Right? So maybe we'll call this lambda 1, call this lambda 2, call this lambda 3, call this vector 1, vector 2, vector 3. Then your solution is just going to be x of t is equal to c1 v1 e to the lambda t, right? Lambda 1 t plus c2 v2 e to the lambda 2t plus c3 v3 e to the lambda 3t. And that's that. That's how you solve this. But remember this. This will save your life. Remember that this doesn't work. See you later. Bye.